Okay, I'm gonna have to resend the stream link to everyone. Uh, new link here. Gonna so you don't just hear me breathing here. Uh, gonna let's see here. Yeah. Yeah. Okay. So now that link is sent, so that people can rejoin if they want to. It'll only be another like 10 minutes of this, but what I was saying is that students will often notice that we are doing computations here that look awfully similar. I mean, we're bringing in these spherical coordinate quantities, uh, yet we're not explicitly, at least it doesn't appear on the surface that we're doing, doesn't appear on the surface, pun intended. Um, So it doesn't appear on the surface that we're actually doing a change of variables integral, but we are. So, well, I shouldn't say that we are. It's that what I should say is that it's accounted for. Um, so this factor that we end up computing, it's not a coincidence that this is the factor that pops out from this normal computation, or this normal associated computation here. Okay. So anyway, um, a couple of other things I wanted to note. So this is a conceptual thing I wanted to mention that some of you might have already noticed. Um, so uh, note uh, if I take g of xyz to be equal to 1, then what is the surface integral of 1 ds by definition? Well, now whatever parameterization I have for sigma, right? So whatever parameterization I have for sigma, I plug it into 1. Well, I don't need to do any plugging in at all, right? Because this is just a constant. So then what I notice is that just directly from the definition, let's go back one more time. Here's my definition for surface integral. Well, now this is just 1, right? So all that I'm left with is this expression. So this is the double integral over R, that's the world where the parameters live, of the normal of R sub u of uv cross R sub v of uv, right, dA. But what is that? We've actually seen this exact double integral before. Right? No, this is surface area. So this is the integral that computes the surface area of sigma. Okay. So why do I include things like this? Just like I included this for the line integral. This shows you how these notions that we're cooking up, right, are related to past notions that we've seen. And it's the thing that, if you were kind of thinking about this as being like discovered in the wild, it tells you that you're on the right path because you have come up with some general notion. It generalizes something that already works, right? So basically it means that this notion of surface area entirely sits inside this this notion of surface integrals. Okay. All right. So what do I do in order to alter this for vector fields? Maybe before I do that, I'll mention one more example that I can do really quickly in a couple of minutes. So here's another example. Maybe we'll reuse the other parameterization we just used. So let's evaluate the surface integral over sigma of 1 plus z ds, where sigma, geez, that wasn't even close. So sigma is the upper hemisphere of x squared plus y squared plus z squared is equal to 1. Or, sorry, is equal to 9. So I'll just reuse the same thing. Okay. So what is my parameterization? So my parameterization is going to be exactly the same as before. It's just all I'm going to change is my theta and phi windows. So what's my parameterization going to be? So this is going to be 3 sine phi cosine theta I plus 3 sine phi sine theta j plus 3 cosine phi k. All I'm changing is that instead of phi going from 0 to pi, it goes from 0 to pi over 2. And theta still goes all the way around, so it's still 0 to 2 pi. Okay. Okay. So where the parameters live does not in any way change this quantity that we've already computed. Right? So this quantity is still very much 9 sine phi. Okay. And so, computing this surface integral, I have the surface integral over sigma of 1 plus z ds is equal to the double integral over r. I can just go ahead and write that in. So this is the integral from 0 to 2 pi, the integral from 0 to pi over 2 of 1 plus z. Z here is 3 cosine phi, so this is 1 plus 3 cosine phi times the length of r sub phi cross r sub theta. So this is times 9 sine phi, right, d phi d theta. Okay. So this is an integral that I can do term by term here. So the first term is going to be 9 sine phi. I can just go ahead and do the integral with respect to phi here. So this is integral from 0 to 2 pi. The first integral is going to be the integral of 9 sine phi. So what's that going to be? So integral of 9 sine phi is going to be minus 9 times cosine phi. All right, plus the integral from of 27 cosine phi times sine phi. So you could take u to be sine phi, that way du is cosine phi. So in that way, this is 27 over 2 sine squared phi. And this is evaluated from 0 to pi over 2 d theta. This outer integral is just going to multiply by 2 pi because there is no theta here. And so what is this? This is going to be 2 pi times, at pi over 2, I would have minus 9 cosine pi over 2, that's 0, plus 27 over 2 sine squared pi over 2. So that's 1. Minus 9 cosine 0. So that's minus 9 there. Plus 27 over 2 times sine squared 0. Okay, so this is 0. This is 0. And so I have 2 pi times 27 halves plus 9. And I'll leave it like that. Okay. All right. So you see how if you already have this term computed, this isn't actually that bad. It's basically like doing a double integral that you're used to, in the early stages of chapter 14. So most of the work that we did on the previous example was actually working through this expression. Okay. All right. So this will show you that a surface integral, and this is a surface integral of a function. It actually gets worse typically. Well, algebraically, I won't say that it necessarily gets worse, but the point is that integrating a vector field is another quantity doing a surface integral of a vector field is another quantity we haven't defined yet. So we'll talk about that next time. And the moral of the story is that we're going to try hard in general to not compute them in the brute force way, just because this is typically nasty. Just like we try very hard to not compute line integrals in the brute force way. Okay, so the next named theorem that we talk about relates line integrals and surface integrals. Okay, in a special circumstance. All right, and then we're almost done. So we basically have like a lecture and a half left in the material. So everything after that will just be review. Your last homework will be posted today, so this afternoon, and it'll be due next week, roughly. We'll say next Monday. But anyway, so that's that. I will see you all next time, and I'll edit the video titles to show that this lecture is broken up into 2 pieces due to my connection dropping for like 3 minutes. But anyway, I will see you all next time.